Morning, everyone. Today, I want to give the presentation about the recent activities of CAS and Atmosphere Analysis Center on GNS and atmosphere modeling within IGS. And my presentation includes 4 parts. The first part is the introduction of the CAS Center, and the second part is for the generation and the validation of the CAS gene. And the third part is for the broadcast model we derived from our center. And the fourth part is for the development of a new RTI map for the monitoring the atmosphere integrated maps. And the final part is for the conclusion. Our center started to study the variation of the atmosphere using GPS from 1995, and in 1997, there's a mistake. This is the 1997, and a new approach for generating the atmosphere TC map over China area has been developed. There's a new method names different area for different stations. In 2004, a new mathematical functions is derived for modeling the local atmosphere TC model, and this mathematical functions can modeling the local atmosphere with more accuracy. And in 2007, a simplified and well-performed global atmosphere model is developed for the Bedou's broadcast atmosphere model. And in 2012, a two-step method named IGG-DCB has been developed for determining the receiver and the satellite DCB using only a few stations. And in 2013, a new method for generating the GAM is developed from our group. And the GAM from 1998 to 2015 has been reprocessed using our new method, and this new GM has been participated to the GM validation organized by the IGS workshop. Based on the validation result, our group has been nominated as a new IGS atmosphere center during the last IGS workshop in Sydney. The new center is admitted by the Academy of Optoelectronics and the Institute of Geodesy and Geophysics, and with the coordinator is Professor Yunbin Yuan, and me and I and Dr. Ningbo Wang is the main researchers, and also we have more than 3 PhD candidates. And this photo shows the Professor Manuel and Angie with our group in 2012. And the second part is for the generation and the validation of the CAS gene. And our gene is calculation using 2 different mathematical functions. And the first function is the spherical harmony functions. This function is used for modeling the global atmosphere TC mapping. And the second function is for modeling the local atmosphere TC map. And the final atmosphere TC map is calculated by combining the 2 different functions. And for example, if we want to calculate the TC at this point, if there's a station near this point, and we will use the local atmosphere model calculated at this station. And if there's no stations near this point, and we will using the global atmosphere TC model calculated by the spherical harmonic function. By this way, based on this idea, and the TC and each grid point, the TC and each grid point will be estimated only using the nearby data, and so as to the accuracy of the TC, and this point will be improved. And based on this new method, the gene in the last 20 more than 15 years have been reprocessed, and the reprocessed gene was validated with 3 different data sources. The first data source is the TC calculated from the GPS station, and this validation result can show the precision of our new gene. And the second data source is the TC from the IGS released final gene, And this is can show the consistence of our new gene with the gene from other centers. And the second is the TC from the altimeter satellite, which can show the accuracy of the gene. And for the validation, we also introduced the gene from other 4 centers for the comparison. And more validation can be found in the poster, also made by our group. And this is the precision result validated by the gene SSTC. And the first group, the first figure is shows the precision of the gene in the global scale with the different centers. And the blue line is the result from our group, and the other lines and are the gene from other 4 different centers. We can find our gene is better than others. This is because we use the local ionophore TC model to calculate the TC and the point in the final TC map. And this table shows the statistics result in different levels of solar actives and in the south and the north hemisphere. And the line with the red letter is the result for Earth, and we can find the precision of our model is better than others, no matter with the levels of the solar active, and no matter in the north and the south hemisphere. And this figure shows the consistency of our GM with the GM from other 4 centers. And the blue line is also the result for us. We can find our new gene is more consistent with the results from the IGS final IGS combined final result. And no matter in around 2000 year and 2016 year. And this is the daily RIS of the difference between the gene from between the genes and the IDS final product. And this is a static table for the last figure. And the last line is for the mean RMIs of the difference between GM and the IDS final product. We can find the mean RMIs of our product is 2.3 TQ, and which is better than the other four GM from the other GM from other four centers. And this is the accuracy result, which is validated by the topic TC. We all know that the topic can translate 2 different singles from the transmitter and the sunlight, and reflected by the C service, and then received by the receiver installed on the sunlight. That's 2 different the singles with 2 different frequencies can use to calculate the TC. And this is the TC. This is the distribution of the topic TC. We can find the distribution is also over the ocean, and which is very advantage to validation of gene over the ocean. Because over the ocean there's always no ground station, ground GNSS station, which contributed for the GM calculation. And this is a table for the statistical results compared with the topic TC. And the red numbers is also the result for us. We can find in the high solar active, our result is better than the other centers. In the lower solar active, our result is better than CODE and the ESA and the DPL, but it's a little less than the gene from UPC. This is the first product published by our new center, and this is the second part I want to introduce to to you, and which is about the refinement of the broadcast ionosphere models. We all know that the broadcast ionosphere model is always considered as an efficient way for real-time single-frequency user to mitigate the ionosphere delays. And the GPS and the Galileo and the Beidou 2 and Beidou 3 all translate the ionosphere models, but with different functions. The performance of the broadcast ionosphere model is limited due to the limitation of the data processing method and the tracking stations number and the distribution, as well as the upload latency is also a very important factor to limiting the accuracy of the broadcast ionosphere model. So we intend to provide the re-estimated broadcast ionosphere model and publish the new coefficients from the internet, and which can obtained by the single frequency user. And based on the new based on this new coefficients, and the user can calculate the ionosphere delay with a high accuracy for positioning. So we think this new this refined broadcast model can be considered as a new precise broadcast like ionosphere model in the frame of IDS. And this is the result with the result of the re-estimation of broadcast ionosphere coefficient. And this is the GPS curve model, and this is for the Beidou spherical harmonic model, which will be used in Beidou 3. And this is the Galileo-Nyquist model, and this is the coefficient we calculate using the global ground stations, and which is different with the coefficients in the navigation message. And this is a global TC map derived from the different broadcast models, which is refined by which is estimated by the global ground data. And this is for the GPS curvature model, and this is for the Beidou model, and this is for the Nyquist model, and this is IDS final GM. If we consider that this the real variation of the ionosphere TC, and we can see that the Beidou model is more similar to the IDS GM, and the GPS curvature model maybe is a little not very more clear. And we also validated our result by the global stations. And this is the result. And we can find the Beidou model is about, the accuracy of Beidou model is about more than 77%. And this is the result validated by the Janssen 1 and Janssen 2 TC. And the Beidou model is also more than 70% of our ocean. And the last product we want to introduce is about a new indicator for the ionosphere integrity maps. And this is the new index we proposed by us, which is named RROT, which can calculate by 3 steps. And this is the result. We compare the RROT to the ROTI and the phase fluctuation. We can find the RROT can capture the ionosphere TC ionosphere integrity period. And we also calculated the correlation coefficient. We can find the ROT index is applicable to monitor the ionosphere irregularities. And this is the result calculated by the global stations for generating the global ionosphere irregularity maps. This two figures is for the storm condition, and this two figures is for the quiet condition. And this is we are a routinely calculation for the RROT, which have been published in our website. And we calculated this product using a more than global 2,000 stations, and using GPS and GLONASS singles. And this resolution in time is about 1 hour. And this is the conclusion for my presentation. And our new center has been published at least 4 different products. The first is for the gym, and the second is for the broadcast transfer models, and the third one is for ROT, and the last one is for the DCB. We have introduced in the last IGS workshop. There is also a short note for our introduction of our new center, and you can find it in the poster room. And the last many thanks to Professor Anjie and to Professor Manu for their help on the discussion, and also for the Dr. Oliver for the help on the DCB calculation. Thanks for attention.